So I'm gonna graph the triangle, and then graph the reflection, and also if you take your pencil, we're going to change this from the line x equals 4 to line x equals -1 as well to make this a little bit easier to do. Let's see. The pre-image D is 0, 2. E is 1, 4. And F is 3, 1. Is our pre-image triangle. And I'm going to reflect this about the line x equals -1. So what I like to do is, when I'm drawing a reflection on a graph, I'm going to draw in the line I'm reflecting it about. Namely, x equals equation is a vertical line through -1 in this case. And if I'm going to reflect this, I'm going to take every point and mirror it across the line. So if I have this line, if D was 1 away from the line to the right, D prime will now be 1 away from the line on the left. If E was 2 away from the line on the right, it's now 2 away from the line on the left. And if F was, what, 1, 2, 3, 4, 5 away from the line on the right, it'll be 5 away from the line on the left. 1, 2, 3, 4. I'm going to have to go over a little bit more.
Wait, yeah, 4.
Did I miscount? 1, 2, 3, 4. Yeah, only 4. That makes life a lot better. 1, 2, 3, 4. On the left is F prime. And voila. We've got a reflection about a given line. You'll see one of the reasons why I chose to do the second example first is because in our first one, we're actually going to get the triangles going to overlap a little bit. So if I graph the same pre-image, and now I'm going to reflect it about the line y equals 2. Where's the line y equals 2? What kind of line is y equals 2? Horizontal through what coordinate? 2. So let's find 2. Draw a horizontal line. So now we're going to reflect every coordinate. Okay, so where should D be reflected to? Yeah, it doesn't go anywhere. The image of D is D prime is the same as D. How about E prime? Maybe 2 under. And F prime, 1 over. So I'm going to draw in blue here to make it easier. So it's been reflected over. Now, I did this example first last hour, and it just kind of difficult to see because it's because they're overlapping a little bit. I think if we choose a line of reflection so that it's not overlapping, it's a little bit easier to visualize the first time. Okay. These are two just arbitrary lines I chose. You can, if we choose a general line like y equals 2, x equals -1, we're likely in this course you're going to have to do it very graphically and draw the line and flip the points. However, there are actually 4 very special lines of reflection that we actually have coordinate rules for, which is our first. The first is the coordinate rules for a reflection over the x-axis. To give you a kind of a motivation for where these rules come from, I'm going to erase these drawings above, and we'll do a little reflection on this. So let's say I have the point, A is at 2, 3. And I want to reflect this over the x-axis. The x-axis here is my line of reflection. What should the coordinates of A prime be? It should be down here, right? So 2, -3. What do you think the coordinate rule, if I had any general point, A, B, what's a reflection of the x-axis do you think is going to be the rule? Okay, I agree. So again, to reflect over the x-axis, I kept the x-coordinate the same, and I flipped the y's. So that's why I'm representing it. If it starts as AB, then it'll end as the same as A, the opposite of B. Okay. How about if I instead want to reflect over the y-axis? What should if the reflection line is the y-axis, what should the coordinates of A prime be instead of this thing? We're reflecting over this line now, so it should be, what did we say, Greg? A prime in this case is -2, 3. So using that to motivate a rule, what's our rule for a y-axis reflection? AB gets sent to the opposite of A, same as B. That's for a y-axis reflection. Alright. Now here's a fun one. I'm going to change the game. We'll go with the point. We'll go this one. We'll work off the point 1 coming through this time, make it a little bit more pronounced. This time, we can also reflect over this line y equals x, which is, does anyone know what the line y equals x looks like? Off the top of your head. This is an important one. You definitely should know what this looks like. Yeah. It's got a y-intercept of 0, so it goes through the origin, and has a slope of 1. So it's a 45-degree angle through the origin. It's the line y equals x. If I chose this as my reflection line, what should the image of this point be? Where should A prime be then? Visually, where do we think? If we're flipping now over this line, where does it look like it's going to end up at? Looks like it should be right here, which is at 3, 1. So if I want to reflect over the line y equals x, AB gets mapped to flip the coordinates. If I want to reflect over this, I'll just simply flip the coordinates. Similarly, if you reflect over the line y equals -x, or the diagonal line on a 45-degree angle through the origin, it'll be very similar, only this time we'll go from AB, we'll get transformed to opposite. We'll flip them and change both signs. Opposite of B, opposite of A. Well, there's 2 examples of this. So if I want to find the endpoints, if the endpoints of this segment is A and B, 3, 2. First, let's reflect the segment using the coordinate rule. Find what the image should be. And then graph both the image and the do the same for the second line reflection. Hopefully you applied the coordinate rules. Let's see, for the line of symmetry y equals x, we'll flip the coordinates, so 2, 3, 1, 4. So if the original was at 3, 2, and 4, 1, then the image is then at 2, 3, and 1, 4. Note that A and A prime are both in the middle, and B prime are both on the outside. This is very important for when you're labeling your diagram. If you flip-flopped how they're labeled, this implies that this is just a translation, it's just a slide. But if labeled correctly, this implies that we have certainly a reflection, because the B's have been reflected. Okay. Same game over here. Let's go, A prime in this case better be, -2, -3. And B prime is -1, -4. So you get 3, 2, 4, 1. And you get -2, -3, -1, -4. Down here. When we get more than just, say, a single point or 2 points that you need to reflect, it can be much more efficient to represent your whole polygon as a matrix and apply a matrix rule to it. There are 2 rules for reflecting this with using a matrix. Okay? So if I want to reflect something about the x-axis, using a matrix instead, matrix multiplication, I could do the following. You could multiply whatever your polygon's matrix is on the left side by this special matrix, 1, 0, 0, -1. This is called left multiplication because I'm multiplying this matrix on the left side of this one. Left multiplication. Multiplying this on the left side. The reason it's called left multiplication, not just multiplication, because if you recall from our discussion when we first talked about matrices, the order in which you multiply them matters. You can't just flip-flop them at random or at will. So if I'm going to multiply something, I'm going to be deliberate of what side I'm multiplying on. And if you're going to multiply with the reflection matrix, it better be on the left side of whatever you're trying to reflect. Similarly, if I'm going to reflect about the y-axis, I'm still going to left multiply my polygon's matrix. But instead, I'm going to use this alternate one. I'll use -1, 0, 0, 1. We'll do the reflection part. So for polygons in general, if we can represent them as a matrix, for example, this triangle, we represent polygon with column vectors. So I'll represent each of these points as a column in my matrix. So P, Q, R would be what? -3, 6, -5, 3, -1, 2. And if I want to reflect this about the x-axis, I could multiply it on the left side by this matrix. 1, 0, 0, -1. And use matrix multiplication to get a new matrix. The image matrix will look like I'm going to take to get row 1, column 1. I think they are, aren't they? 2 by 2, and this is a rows by columns. So unfortunately, you still can multiply. So if I went row 1, column 1, I'll take row 1 and multiply it by column 1. So 1 times negative 3 plus 0 times 6. It's just negative 3. 1 times negative 5 plus 0 times 3. Negative 5. 1 times negative 1 plus 0 times 2. Negative 1. Row 2, column 1, I'll get 0 times negative 3 plus negative 1 times 6. Okay, and then the wild guess, continuing this on, the second one will be negative 3, negative 2. And this matrix, notice the difference between our pre-image and the image matrix. What did it do? What's the difference between our pre-image and our image? The bottom row's signs have all changed, corresponding to flipping the sign of the y-coordinate, which is the same as the coordinate rule that we just had. This is two equivalent ways to create a reflection. Now, once you have this image matrix, now you know what P prime, what Q prime, and what R prime are, these column vectors. And now you could plot these points as well over there. In the interest of time, I'm going to skip graphing this, but you can do it on your own. We can. Oh, I guess I can't remember if I told you if I mentioned this already. Reflections are isometries. Did I say that? Reflections are isometries, so they maintain the shape and the size. Similarly, rotations also are isometries, and there are two different ways to represent. Again, we have coordinate rules, and I'll have some matrix rules below for rotations. There's really 4 rotations you could do. Well, there's an infinite number of rotations you could do. In this course, we're going to work on just 90, 180, and 270 degree rotations. If you want to rotate at some other angles other than those basic ones, you're going to need some trigonometric, some trig background, some sine, cosine, angle stuff that we're not going to get to. That you'll get to eventually when you move up the ladder. Coordinate rules for rotating. So if I want to take a point and rotate it at a quick 90 degrees, I'm going to do the following. And note, I don't have these memorized. Which is kind of why I don't expect you to have them memorized either. So, AB is mapped to negative B, opposite of B, same as A.
Wait, what?
If I want to rotate an object 90 degrees on a plane, I can apply the coordinate rule, 90 degrees about the origin, excuse me. I can map it to flip them in opposite of B. For 180 degree rotation, opposite of A, opposite of B. And if I want to go a full 270, well, I'll go same as B, opposite of A. What's that? The boxes below are going to be our 4 matrix representation. So again, we can rotate individual coordinates with these rules. It can be more efficient if we have larger polygons to just use the represent as a matrix and multiply with matrix multiplication. The matrix rules are as follows. If I want to rotate 90, I can multiply by this matrix. Rotate by 180. By 270. And if I want to rotate in a full circle so that it has not changed, you could multiply by the identity matrix. 1, 0, 0, 1. So we got a couple examples here. You can do whichever you'd like. I recommend doing at least one of these using matrix representation. If you have noticed that I have one that doesn't ask you explicitly to use matrices, the second one does. So I would practice at least one, if not both, using matrices because that is kind of a new way to think about these. But you have we still have about 5 minutes left in class. So I'd like to see if you can get work on these right now. I'll come around and check where we're at.